Hello, welcome to another virtual star party for the Fort Worth Astronomical Society. I'm your president, Chris Modnitsky. It is cold. It is unseasonably cold for the middle of April for North Texas. We had a lovely weekend. It was, I think it hit middle 90s, 93, 94, and it's not that anymore. So, dressed up here and got a hat on, got a jacket on, zipping it up because we're going to be at it for a couple hours. So we're going to do something a little bit different today. It's not just going to be me. We have some other members of the Fort Worth Astronomical Society here. So let's see if we can get this thing to work. How is this going to work? There we go. Hey, all right. So we have on here, see, George Lutch, we have Robert Cargill, we have Dave Cox. We have other members from the Fort Worth Astronomical Society. Say hi, everyone.
Hey. Hello, everyone.
I hope that audio goes out on the Yahoo chat. If you can go ahead and let us know if you can hear them talking, that would be absolutely fantastic. It's our sanity check to make sure everything's going as it should. We did have some technical issues earlier. We're still trying to work them out. I'll go ahead and say it. I forgot to take the lens cap off of one of my devices, and so I couldn't get my scope aligned. So we're waiting to get that thing fixed. Once that finishes up, and it should be any minute now. Yeah, now it's aligned. See, it doesn't take 20 minutes to align a telescope if you do it right the first time. But here we are. So, what we're going to do now, we'll just go ahead and get right into it. So, what we're doing right now is having a virtual star party for anyone who hasn't joined us before. Typically, what the Fort Worth Astronomical Society does is we'll have a public event. We'll have it at Tandy Hills, we'll have it at Dinosaur Valley, we have it at various other places, at libraries on occasion. And we'll bring telescopes out to the public. We'll let the public look through them. Be able to see typically nebula, the planets, galaxies, stars, double stars, open clusters, globular clusters, anything we can see in the sky from a suburban environment. We can't do that anymore because of the COVID-19 crisis. We are now stuck at home. So this is about the best that we can do. We still do want to bring the night sky to the public. We just have to do it a different way. So I've done I think this is now the third virtual star party. I think this is the third virtual star party now. So we're going to keep doing these up until the crisis is over, and we may actually do some of these with just continuing on after everything is done and finished, because they are kind of interesting, and we'll be able to actually show some stuff that we can't typically see in a suburban environment by going out to one of our dark sky sites. And we can't really bring 150 to 250 people out to the middle of nowhere safely yet, but maybe we'll do that in the future. This will be one of the ways we can actually take people out and be able to see things like galaxies and very dim nebula. So today, what we're going to do is grab some images. We'll take a look at some objects in the sky for the next couple of hours, and then we'll also switch over to George, Robert, and Dave, and they will go ahead and show what they have on their cameras, on their telescopes. The internet is a pretty cool thing. I can tell you about 20 years ago, none of this would have been possible. But now we can actually do things like this. We can bring the night sky to you. You are sitting in your living rooms or in your offices, or curled up in bed with a nice warm cover on and a cup of hot chocolate or hot tea, which I wish I had thought of bringing, which I didn't. While we're out here in the cold, suffering just for you. That's about as cheesy as I'm going to get. So let's go ahead and get started. I'm going to switch over to desktop view. The reason I'm doing that is we're going to show some various objects, and technical difficulties. I haven't started on this yet, so we're going to go to, I'm going to bring up an application here called Starry Night. Starry Night is a application that is it's a virtual planetarium. It lets me do a whole bunch of stuff, not just control the telescope, but actually, go back. It lets me actually look at the night sky at any point in time on the Earth, on any planet in the solar system, from any position on its surface, or hanging out in the middle of space, and it lets me control the telescope. That's what I'm going to use right now. So I have everything connected. Now hopefully this will work. But we're going to be looking at a couple of objects, and it's much easier for me to go ahead and do this connected to the telescope from the computer than it is for me to just go ahead and fiddle with the handset and play with it and struggle and get annoyed and say things I probably shouldn't say. I just have to make sure this works. And this worked last time. I'm hoping it'll work this time. It looks like it's okay. Come on. All I have to do is hit connect. All I have to do is hit connect. And it works. Fantastic. I'll drag this over, and I'll drag this over. It's not bothering anybody. So what do we have right now? I'll be honest, it's really hard for me to see what's going on right now. And the reason why I say that is because I have a very bright studio light right here shining in my face so that you can see me, so you're not talking to someone sitting in the shadows. But that absolutely does kill my night vision, so the only thing I can see right now pretty much is Venus. So let's go ahead and take a look at Venus. We'll do that first. This is kind of our test, so we're going to swing past Orion, and we're going to hit Venus. We're looking into the west, and I'm guessing that is Venus right there. We're going to turn on some labels. I want to get clusters. I want to get NGCs, and I want to get planets. Where's my planets? Planets, moons. There's Venus. All right. So what we're going to do, zoom in on Venus and see what it should look like. It should be a crescent. Cool. So I'm going to click on it. I'm going to center Venus, and I'm going to hit slew to Venus. And let's see how close we can get to it. So what I'm doing is I'll switch over to a different view. Let's go back to, here we go. So in the background, I have my telescopes. Actually, I have two telescopes on there. One is a 4-inch apochromatic refractor, and the other one is an 8-inch Ritchie Crichton. It's the same optical design as Hubble uses, so I believe it's two hyperbolic mirrors. One is a wide field telescope, the other one is not a wide field telescope, it's narrow view, but we can get two different images, two different views out of it. I had issues with one of them last time. We will see what this time it's going to be like. So let's switch back to this view. So we can see this is what Venus is going to look like, and I'm supposedly tracking on Venus. Now I need to open up a different application, and let's see what this does. I'm terribly sorry for not having this up and running already. I actually had to reboot right before we started, so I'm just bringing everything back up. The application that we're switching to now is called Backyard EOS. This is a really nifty program that will let me connect into my cameras if it opens up. There it goes. So Backyard EOS is it's just an application that connects to a Canon camera. It's just Canon specific. There is a Backyard Nikon as well by the same software developer, and it connects to Nikon cameras. So it will let you do absolutely everything. You can configure the camera settings however you want, and it will download the images directly to your computer, so you don't have to keep everything on the chip. So we'll go ahead and do that. There we go. So connect in. All right. It's only saying one of my cameras. Okay. It's not great. It's okay. It's not great. I'll have to switch to something else. So let's do Planetary. I had decent focus on it earlier. We'll see what the focus can be like now. There we go. So this is not bad. It's not horrible, but it's not great. So let's go ahead. Well, I'm going to go ahead and center it out. So there is a reason why I use a hand paddle. Oh, wrong direction. Better. The reason why I want it centered out is because I can do a reset in Starry Night and be more accurate later on. Okay. Come on. You always hit the wrong buttons, don't you? Alright, there we go. That's good enough to be centered. And go ahead and expand it out. Really? 5x. There we go. So this is Venus. It is... see, cut down that shutter speed a bit more. Venus is very, very bright. So if I try to go in and do something... here we go. If I try to use a longer exposure, it will just... Well, let me show you. I'll do a much longer exposure. We can see that if I do it even more. Let's do 1/5 of a second. Wow. That's just a lot of detail, isn't it? You can see everything there. We don't want that. So we're going to cut down, way down. Let the camera do the work. Hope everyone can see that. We're looking at now a crescent Venus. So previously, at the first star party when we looked at Venus, and at the second one, we were looking at a half Venus. And the reason is Venus reached its greatest eastern elongation, which means it was the highest it was ever going to be in the western sky in its orbit. So we saw half a Venus just like we would see a half a moon. It is now past that, and it is swinging back towards Earth. And because it is, for the next several weeks, we will see it not only go further down into the sky, closer to the sun, and it won't be up as high after the sunset, but it will become larger, and it will become a thinner and thinner crescent. It will actually become a little bit brighter. Its brightest point is not when it's when it is a full Venus. It's just when it's closer to us.
Hey, Chris.
Yes.
This is for Robert. He may want to mute because people are saying they're hearing echo.
Oh. Robert, can you mute your mic?
Sure. I don't see no picture of Venus.
Oh, because I'm not sharing with you. See, technical issues. So, let's see if I can do a share screen with you guys. I'm not sure if I can. Share screen one. Let's see if this works. Okay, can you guys see that now?
Yeah, we can see it.
Okay, cool.
Yes.
So this is going to be weird, but somehow it'll work. Okay. So, guys here can see Venus, and you guys here can see Venus. All right, we're good for that. All right, so that's really all we can see with Venus right now. It is actually a really nice night. It is clear looking out toward the horizon this afternoon. We don't have a whole lot of pollution going on. It was clear all the way to the horizon, and that's kind of rare for April. It's kind of rare for North Texas, so the skies are nice. They're rather still. I don't have much of a wind. It's a very, very tiny breeze. Looking up at some of the stars, there's a little bit of a twinkle, so the sky is pretty still. Hopefully we'll be able to see some decent images. This is actually really typical of what we see with planets. It's kind of flowy, and there are techniques to do to take photos of planets, which we're just not going to get into today. We've got a lot of stuff to do, so let's see. Echo started again. I know why. How's this? I think now the echo should be gone. I'm not broadcasting the echo right now. Okay, I think this will do, and then I will have to figure out a way to turn it up and turn it down as needed. Okay, any of you guys have anything lined up yet, or should we go ahead and go to the next target?
Still T-pointing, so...
Okay. And Robert, you got anything, or we're going to wait?
Well, right now I just got an image of the North Star. I'm taking about 60 frames of it right now.
Okay, that'll work. So let's do this. We talked earlier about what we're going to look at. So there are a couple of objects we wanted to go through. We have toward the west, and I think I'll be able to pick this up. This is M35. M35 is an open cluster. Let's go ahead and take a look. So we want to look at a few things tonight. We're going to look at M35. This is an open cluster. We're going to look at Comet ATLAS C 2019 Y4. It recently broke up over the last couple of days. There are at least 3 fragments. We're going to see if we can spot the fragments today. And we will go ahead and look at the Christmas tree cluster. It's another open cluster. We will look at M3, which is in the western, off toward the west, so we should be able to see it pretty well. And this is a globular cluster. And then I believe we'll look at what else? M101. Robert is imaging. Robert, what are you imaging tonight?
Well, right now I'm just doing the North Star, but later I will be doing the cluster in Virgo.
Markarian's chain. That's it.
Yes.
So Markarian's chain is a group of galaxies. They're not necessarily next to each other. In fact, they could be separated by long distances, one very close to us, one very far from us. But they're all together in the same part of the sky. Yeah, and the neat thing is it's called Markarian's chain after the guy who discovered it. But it's a chain because you can start at one galaxy and just go to the next galaxy and the next one, the next one, the next one, the next one, and you barely have to move your telescope. You have a bunch of them in the field of view at the same time. So we'll take a look at that. Now let's go ahead and jump to M35, and while that's doing its thing. M35. Okay, I'm looking at M35, and I'm going to hit slew 2. So we're going to move, jump out. Where did it go? Well, there's a California, but I don't think we're going to see it well. And backyard, up to here, Planetary. I don't want that. I don't want Planetary. I want regular imaging or frame and focus. Let's see. Let's do frame and focus. This will do a quick video. I can see what this looks like. I'm not seeing anything because we got to go. Yeah, we need much longer exposures. So now that we're looking at stars, we want much longer exposures. We want much lower ISOs. We want to be able to see what's out here. If there's anything, I got something. Had something. Little star right there. Probably need a longer exposure. 2 seconds. Yep, we got a little star right there, so it's twinkling a bit. So we're fine. Okay, I think on the focus we're going to be fine. I'm not sure where we're pointed at. We got to figure that out. And where is... Did I lose my connection? No, I think I got my connection. I just don't know where I'm looking at. What am I looking at? M35. I did slew 2, so let's do center. We're going up. Okay. Cool. M35 open cluster. So I have that should be in view right there. So one of my issues here is that I am on the eastern side of my house, and my house blocks almost all the western sky except for a small little sliver from where I'm looking. So we're going to do this now. We're going to go ahead and take an image, get out of planetary images, and we're going to do standard imaging. This program will go ahead and let me set this up however I like, and I'm going to do a set it for bulb. I'm going to do, just to start off with, I'm going to do a 30-second exposure, ISO 1600. I just want to make sure it's in the field of view. I want mirror lock, save to PC, camera, blah, blah, blah. We're going to say this is M35. And do I have a filter on there? I got something. Doesn't matter. I'm going to do one capture. Now what's going on is that the camera shutter opens and it stays open for 2 seconds, and that eliminates that little bit of shake. Then it'll take a 30-second exposure. Once the exposure is complete, it will go ahead and take another 30-second exposure, and that is the dark frame. So what that means is the second exposure will be automatically in camera subtracted from the first exposure, so I get rid of a lot of noise. And I'm guessing I'm going to have a lot of noise on this first image because I had the camera open, I had the chip going in video mode, and that makes the chip very, very hot. I think we'll be looking at 40 to 50 degrees Celsius for this image. We'll see what that looks like once this is done. Another 20 something seconds. So we've got to gotta wait. Just gotta wait. In the meantime, I will switch over to something else. Let's see, is this PhD? Yeah. So I will swap this over to another screen, because what I want to do for that, that's not really what I wanted. What I want for that one is, that is my auto guider application, and what I have to do with that is get it all configured. Okay. That means it's done. Now we wait a couple seconds for it to download. A couple seconds. Any minute now. Any second. This is the life of the amateur astronomer. We sit in the cold and wait for our images to download. Oh, they better download. Oh, come on. It can't be that slow. There it goes. All right. We are close. We are close. We are not exactly there, but that is fine. Let's see. Do a recenter. What am I looking at? I'm looking here at M35, and we have NGC 2. What is that? 2 something or other. 215856. It's kind of hard to read. Let's see. Function. There we go. 21502158. Okay. 56 or 58, something like that. So we have a small cluster here and we have a larger cluster here. So we're looking at the larger cluster first. There we go. So this is the smaller cluster here, and this is the larger cluster up here. So cool, we were actually able to get both. And let's see what this looks like zoomed in. All right, so I'm not tracking too well. You can see that the stars are kind of smeared out. That's fine. Early days, early night. But I wanted a nice 30-second exposure just so I could frame it, just so I know where I'm looking at. And this is centered. If we're looking at the center right there, that means on here, we are centered roughly right there. So I will click this and I will say, center that. No. Where is it? Not slew to this location. There is supposed to be a button that says recenter. Sync. Sync on that? Is that it? No. You know what? It's going to be good enough. I'm not terribly worried. We're getting it in the field of view. So that's where we're pointed at. Want to see the whole thing? We've got it. So this is, again, a 30-second exposure. I have a light pollution filter on there. You can see the background isn't black. The sky here is just not black. This is suburban skies. But the filter that I have is cutting out a lot of the light pollution. It actually lets in very specific bandwidths of light. We want the light from stars. We want the light from nebula. We want the light from galaxies. We don't really want light pollution. So we block everything but the stuff that stars and nebula emit. There's some stuff we can't really do in the city, but here, well, we're doing the best we can. So this time I'm going to do a 1 minute exposure, but I'm going to set to 800. I want less noise in my image. I want to see if I can make it a little bit darker, but I want a longer exposure because I want to pull out more data. So what I'm going to do is hit another capture and let it go. So this will be 2 minutes of me sitting around. So while this is going, I'm going to bring up my tracking application on a different screen. It'd be nice. I should bring a mouse out here. I really should. I'll go ahead and bring it in here so you can kind of see what's going on. I'm looking for a star. Any star. Any star whatsoever. I don't know about y'all, but I don't see any stars in that field of view. This is a guide camera. 3 second exposure is way too much. Let's do 1.5 seconds. What a guide camera is, it's a well, it's a little camera. It sits on a guide telescope. The guide telescope lets me track on a star, and I will show you how that works as soon as I can find a star. Yes, Robert.
If you try, I think it's out, select out and S, I think it automatically find you a guide star.
Oh, no. I'm out of focus. That's why I have no stars.
Oh.
I now have to go and focus the telescope. So hang on a second.
I was going to tell you to take the lens cap off. I've never done that.
Let's see. Here we go. Yay! How's that? Are those nice sharp stars? Those are sharp enough for what I need. All right, cool. So what we've done now is got everything in focus. And once everything is focused, it is nice and sharp. So we have an image that was just taken. That is cool. Here's what I'm going to do. We're going to train it. So I've got a star here. And it's a nice, decently bright star. Found it, and PhD. I will do begin guiding. It will go ahead and now train it. So PhD stands for Push Here Dummy. It's a really simple program, and what it's doing right now is it's training the system. I think it's training the system. No, I need to stop it. Stop it. Stop. What I need to do instead is I need to clear the calibration. Clear. Modify calibration. Clear calibration data because this still had the calibration from last time. And I have to go ahead and let it train it. So what it's doing is it's locking onto one star. And then it's sending a signal to the mount saying, move here a little bit. Move in this direction. Right now it's going west. Then it calculates how far the star moves when it pushes the mount to the west. When it's done, it pushes it to the east, like it is right now, and it figures out how far does it go to the east. Then it does north and south. And once it knows how far it needs to push, then it can keep that one star on 1 or 2 pixels on the chip, and it will result in very accurate guiding, I hope. And we won't have smeared out stars. And this is how guiding is done on most amateur level telescopes. Your mounts aren't super accurate, and so you use a guide scope and a guide camera in an application like PhD to let you do nice long exposures and get those really, really pretty images, some of them we'll be seeing later on. So that's the thing finished. Guiding, cool. It is guiding now. I will clear out my graph. Let's see how this looks. It's starting, so it's not horrible yet, so it's fine. We'll let it settle out some. It's doing it. It's doing something. Cool. Let's let it finish. Or I can do 1 second, a little bit faster. Faster corrections. We'll see how that goes. All right, let's go back to Backyardios. Let's take a look. So this is actually quite comparable. This is what I was expecting, just a little bit less noise. If I look at it, we'll go ahead and zoom in. See a lot of color noise in the back. Bring this one up, see what the difference is. There's a lot less color noise. You can see a significant difference because I went from 1600 ISO to 800 ISO, but in order to get a very, very similar image, I had to double my exposure. So I went from 30 seconds to a minute. Let's go ahead and get up to, I want to do 2 minutes. Let's do 2 minutes. I want to see what stars we can pull out. If we look here, there are a lot of really dim stars all through here that we can just barely see. They are coming out of the noise though. If we go to the other one, which remember it was a shorter exposure, it's harder to make out some of these stars. I think there's something here, but it's lost in the noise. There's stuff in here, but it's getting lost in the noise. It's hard to make out. So when we're doing photos like this, stars come out when we do a longer exposure, lower ISO, to get rid of that in-camera noise. The way that DSLRs work, the way pretty much every camera now works, when you have ISO settings, it's not true ISO like it used to be with film cameras where you had grain sizes. What it is, it's electronic gain. So it's taking the same image, it's just electronically boosting the levels, and it's boosting the noise at the same time. So when you're doing something like daytime photography, it's not a big deal. The noise isn't a really big problem. When you're doing nighttime photography with long exposures and your chip is getting warm, then it's an issue. And you can see on here, the chip's at 23 degrees Celsius. That's a pretty warm chip. I can tell you, I wish my hands were 23 degrees Celsius right now, because they're not. I don't know what the temperature is, but it's chilly. All right, hang on. What is the temperature? 51 degrees. I don't think it's 51. I think it feels significantly chillier than 51 degrees. Nonetheless, that's where we're at. So we got another 15 seconds left on the exposure, so I'm not touching anything. Jump to PhD real fast, see what that looks like. Graph's not horrible. It's not great. It's not horrible. It's fine for tonight. We're not taking any fantastic images. We just want to see what we can get. And I also want to see what we can pull out down here. Let's zoom in again. Go way down. This is the other NGC cluster, and we can see some red stars in here. When we're looking at stars, what we're typically seeing in the sky is blue, white, and red. If they're closer, we may see them yellow, orange. But typically, we don't see large stars that are yellow or orange. We do see large stars that are red, the red supergiants, red giants. We see blue and white stars because those are, again, very large stars, but they're very hot stars. If you look at the life cycle of a star, it starts off as a nebula, and something happens, it accretes, and collapses down into a star. If it's small enough, it's a dim red star that's very hard for us to see. If it's the mass of close to our sun, then it turns into what's called a yellow dwarf. It is a rather small sun in comparison. If there's too much mass, then it becomes a white giant, or even a blue supergiant if it's enough mass. And then when a star our sun size dies, it turns into a red giant. It's very large, but it is fairly dim. It'll be brighter than our sun, but it's still fairly dim compared to other ones. If you look at bigger stars, much more massive stars, they turn into red supergiants. And Betelgeuse is an example of a red supergiant. It's the big red one in in Orion. And we can't see it now because it's ducked down below our my roof line. So a couple more seconds, and here we go. So when we're looking at this cluster here, we have some bright stars. This is a bluish star. These are red. It's hard to tell just from this if they're red because they're actually red stars, or if they're red because of the distance to them, along with a dust cloud in between that can also redden stars artificially. Okay, the background is a lot brighter in comparison, but we're able to pull out so many more stars. Let's look at M35. Yeah, we can see a whole lot more stars here. Let's just take an example right there. Compared to the other one, we can see a couple in here just barely peeking through, just a little bit. And then when we jump to the longer exposure, now they're coming out. They're definitely coming out of the noise, even more that we didn't even see before. There is additional color noise that we're picking up, but we are able to see more. Let's see if I can drop the histogram down. Yeah, we still are able to see some of these stars that we could not see before. So that is pretty cool, especially if I pop them more like this. Now we're popping some of the noise out as well. I can get rid of the color and just do luminosity. Let's see if that helps. It helps us a little bit. If just do a black and white view, we can kind of see the stars coming out. Let's switch back to RGB, and we'll reset that so it doesn't look too artificial. That's kind of neat. And let's go down to the NGC cluster, and it's not quite in focus. I think I can fix. Actually, what this is a little bit of coma in here, which is a whole less than what it would be without the field flattener. But coma means that because of the optics, because of the curvature of the mirrors, stars on the very edges of the images, it looks like almost a little comet. It's like that little point. You can see, like with this one, there's a little point right there and a little streak to the back. It's just the way the telescope works. There are corrected telescopes, there are uncorrected telescopes. It's just the way they work. This one happens to have coma. I can have a coma corrector on it. And actually, I think it needs a little bit of help with collimation. Not a whole lot, though. The center's pretty good. No, it needs a little bit of collimation. On this side, it looks like it's okay. And it's on the other side that there's a little bit of coma. So it's that's what it is. Ignore the spot right there and those spots. Those are actually on my chip. I have to clean it. I haven't done that yet because I don't have time right now. And on some of the brighter stars, there we go. So you can see these veins coming off of the star. If it's a bright enough star, you will see it here as well. And these are diffraction spikes because I have 4 veins at the front of my telescope which hold the central mirror in place. And what you're looking at is a quantum mechanical effect as the photons actually go around that vein, and it creates what are called diffraction spikes. And you see them along the axes of where those veins are. So if I had one vein sticking out that was holding that mirror, you would see 2 spikes, one out of either side of the star, because these are always symmetrical. If I had 3 veins coming in, I would see 6 spikes. And if I wanted to absolutely minimize it, there are actually some curved veins. It looks like a little half circle that attaches to the side telescope and holds the mirror in place. And those are actually pretty neat, and they minimize the diffraction spike by spreading it out. It's still there, but it spreads it out. So it depends what you want your images to look like. If you don't want them to have any spikes whatsoever, you can use a refractor. Unfortunately, the camera on my refractor doesn't seem to want to talk to anything, so I don't know what's going on yet. As I can't talk to the computer, and my other camera died a couple of weeks ago, so it's not running at all. Okay, so we've seen an open cluster. Anyone have any questions? There's about a 10 to 15 second delay on on what I am saying and to the point where it goes live. So if you type something in, I will get to it as soon as I can. George, Robert, Dave, you have anything to add? Have anything to say?
No, not right now.
All right, we can go on. So this was M35. Let's go on to the Christmas tree cluster. The Christmas tree cluster is going to be a ways a bit. See if anything interesting. Christmas tree cluster, here we go. Well, I'm hoping I can see it. I should be able to. The Christmas tree cluster is called that because it kind of, sort of, looks like a Christmas tree. This one on its side. And I should stop guiding as well. Why didn't I just stop guiding? Because it lost all its stars. The nice thing about having a little guide scope like this is I can use this thing as a finder as well. Okay, somewhere there. I don't know where. I don't think I had the guide scope perfectly aligned. That's fine, but this should do it. I'm going to pick out another 120 seconds exposure. Or actually, better yet, I need to start guiding. Pick a star, any star. That star's good enough. Let's go ahead and guide on that. Give it a couple seconds, make sure it's got it. Cool, that'll work. Jump over. This is really. Okay, Christmas tree cluster. And the only reason why I do that is because it saves the file name with that, so I can actually keep track of it more easily. Anything else interesting over here? We have some amp glow. This side of the chip here. This is a feature. It's just from the way the chip is manufactured. On this side of the chip is where most of the readouts are, and you have what's called amp glow. It's an electronic effect. It's basically heat and electronic noise from that side of the chip is changing the way the image looks. On your point and shoots, even on your DSLRs, if you're taking regular daytime pictures, you don't see any of this stuff. This is only stuff that you see that's going to be for long exposure images. And speaking of long exposure images, next week on April the 21st at 7 p.m., we will be having our second virtual monthly meeting. We're not having meetings at least until probably June, if not any longer. So we'll be doing virtual meetings. I'm trying to replicate exactly as best I can what we do in our regular monthly meetings. So if you haven't seen it, I have a stream ready to go for that. We'll go ahead and publish that. Actually, that is published on the Facebook page now. I did that earlier today. You'll be able to see the meeting. You'll be able to interact with the live chat. And we'll go ahead and try to do it the same way we did before. I'll talk about current events, what's going on in the club, the elephant in the room, and go over the astronomical events for the next month or so, month and a half, so that we know what's coming up. I will then go into a presentation, and I think we have a special presentation. Jerry Gardner is one of our club members. He is a very accomplished astrophotographer, and he will be giving a presentation on astrophotography on a budget. So no matter what your budget is, there will be an option for you. If all you have is a DSLR and a tripod, you can take astrophotos. They won't look like this, but they will be astrophotos. And then if you have a whole lot of money, more money than you know what to do with, he will have options for you as well. I don't have that kind of money, so I do the best I can with what I have. But this is actually kind of neat. You can actually see things with the camera that you could not see with the naked eye. The camera records photons. So as the As the mirror is open, as the chip is exposed, it counts every single photon that's hitting it. Um, so every time a pixel gets hit by a photon, it adds it to the register. Then, when the image is complete, it adds up all the registers for all the pixels and outputs the image. There's some more math involved. You have the Bayer filters and everything for color, but that's the basic way that the chip works. Your eyes don't work that way. When a photon hits one of the rods or cones in your eye, it changes the shape of the protein, sends a signal along the nerve to your brain, and then it resets itself. Every single time it does that, takes a photon, changes, resets itself. Changes, grabs a photon, changes, resets itself. Because of that, it's not additive. We don't really have great night vision because while those, is it rods or cones? I'll say it's rods or night. Anyway, while they're very sensitive to light, can't see color. So everything is black and white, essentially through the eyepiece, and you only get the photons that happen to be hitting your eyeball at that time. There we go. We have the Christmas tree cluster, which is right here. It looks like Christmas tree. If you look at it, here's the bottom and here's the top. Or is that the other way? Oh, no. Here's the bottom and here's the star at the top of the Christmas tree. And there's actually some nebulosity in here as well, but in suburban skies it's really hard to pick that out, especially because we have such short exposures. We're only doing 120 seconds. If I had knocked my ISO down, we had darker skies, and I did something like a 5-minute exposure, that nebulosity would really come out. But I'm pretty sure it's hard to see. Let's go ahead and see it right there. So we're picking out some of these dim stars. I don't have perfect focus on this thing, but it's not too bad. It's really not too bad. Getting only a single spike. I'm not going to worry. That's not perfect. I'm going to see what I can pull out here. Yeah, it's too dark. Yeah, I can't get enough. I can't get the nebulosity out of it because we just have too much light pollution. Yeah, I'm just not getting it. Just not able to pull it out. I just don't have a long enough exposure. But we are seeing nice round stars. There's a tiny little bit of elongation, but it's not much. I'm not going to worry about it. See, I think this is a hobby that should be fun. It should be exciting. It should be interesting. You should be able to see really, really cool things and should be able to talk about them. So, an open cluster. What is an open cluster? For anyone who doesn't know, an open cluster is just a group of stars in the sky. Typically, these are formed from the same nebula. Think of them as sibling stars. They form from the same material, so they typically have the similar compositions. They may not have similar sizes. You may have really small stars, you may have really, really big stars, and that's kind of dependent on the density of the nebula where that star was formed. But they're all made of the same stuff that the nebula was made of. So they have similar, very, very similar proportions of hydrogen to carbon, to nitrogen, to oxygen. Whatever was in that nebula, that's going to be the percentages of material inside the stars. So sometimes we see them with a lot of nebulosity, like if we're looking at the Pleiades cluster, there's still remnant nebulosity around their dust clouds, and the light is shining off that dust clouds. Others, like the Orion Nebula, it's an active star-forming region, so there's constantly stars forming in there. And the nebula, the gases are still there, and those hot young stars are lighting up that nebula with ultraviolet light. They're causing the gas to fluoresce, the hydrogen, the oxygen, and the sulfur, and nitrogen if there's any. But with open clusters, they're typically a lot older. The nebulosity, for the most part, is gone. All that gas is gone. It's either used up or it's been actually blown away by those stars. They're young, they're massive, they're hot, they're putting out a lot of radiation, a lot of ultraviolet, and there is I can't remember that name, POY, pointing radiation, pointing effect. I can never remember how it's pronounced. It is it's a sweeping effect for dust and gas from the vicinity of a star. When that star first lights up, when fusion starts going off and starts pushing out photons and solar wind material just going out, it pushes the dust away with it. So you see this clearing of the area around a star. When our star first formed, we had an accretion disk that was full of dust. All that dust has been pretty much blown away in the last 4.5 billion years. The sun just pushing out solar wind, pushing out light. That light actually has a mass, and it's pushing away all that dust, and it's clearing out the area around the star. Something similar is happening with these open clusters, where you have all of these stars pushing this dust away, and as they're moving through the galaxy, the dust gets further and further from the star, and the gas gets further from the star. It's no longer being lit up by the ultraviolet radiation. The stars settle down after a couple million to a couple billion years, and they're not putting out as much radiation as they did when they were very, very young. But that gas is now far away. That's no longer fluorescing, so you don't see that. And with the Pleiades, you don't really see any fluorescing gas around there. What you see is the reflection nebula. It's dust, which is still a remnant around there. So we don't see a whole lot of nebulosity with the Christmas tree cluster, even though there is nebulosity going on with much longer exposure. So we're going to take one more image of it and see if any more details come out. But I'm actually pretty happy with that. We're able to see a little bit more detail than I expected, and especially with the 2-minute exposure and lowering the ISO, we're able to pull out some stars that we otherwise couldn't see very easily. Sorry, I'm in my backyard, so I have to, there are dogs, the highway is not too far away, so there's still a little bit of traffic on there. The neighbor's pool pump is going. I hope you can't hear that, but it is in the background and I can hear it. And I hope I'm not bothering my neighbors too much by being out here at 10 o'clock at night talking. I'm just not talking very loud, but I hope you can pick me up pretty decently on the audio. Got the gain turned up a bit. All right, George, Robert, Dave, you got anything going on yet? Anything you want to show off?
Just about to start imaging in 51, so give me about 5 minutes, and I can take you through what I've got.
So while this is going, for another 2 minutes or so, you have a couple of options when you want to do astronomy. You can either have a simple telescope, or you can have a complicated system. If you have a simple telescope, it becomes much, much easier to actually grab your telescope, go outside, start looking through it. If you have a complicated system, it takes a while. I will say, on the average, just for me to get the telescopes set up, to drag everything out of my office, take it across the house, bring it to the backyard, set everything up, just so I can start taking it out. Put everything, set up the mount, level it, get it roughly aligned to north, put the telescopes on there, get all the cables connected, is easily a 45-minute job. Once I have the cables connected, then I have to do some alignment tricks. I have to do a polar alignment. I have to make sure the telescopes are both pointing at the same object. I have to do a lot of stuff, and that usually takes another half hour to another 45 minutes. And I also have to wait for the sky to get dark. So right offhand, I know I'm looking at 1.5 hours setup time each time I want to do this. Once I have it set up, then I have to start taking images. Well, what do I have to do? I have to do the guiding. I have to get my cameras ready. I have to make sure I'm looking at the right thing. I have to realign stuff. Easily another half hour or so. And that's if I'm not going too fast and make a mistake and forget to do something like I did earlier, not take a lens cap off my alignment scope.
Chris.
Yes.
I got a picture of the Christmas nebula. If you want to.
Yes. We will do this. Robert, if I will go ahead and stop my share. Robert, if you want to go ahead and share yours, I will move it into place. Okay. Ooh, that is very lovely. Wait, was I totally wrong? Was I totally wrong? Is that bright one at the bottom of the Christmas tree? I was wrong. I was wrong. Yeah, that's the one at the bottom of the Christmas tree. So
Actually, the star right up, see the Cone Nebula there? I think that's the Christmas tree,
that's the Christmas tree?
isn't it?
I thought the whole thing
Or
was
is it the whole thing down here?
I thought the whole thing was a Christmas tree and that was just the Cone Nebula.
Or something.
Yeah. So this is called the Cone Nebula. Robert, can you zoom in on the Cone Nebula real fast? All right. So it looks weird because this is actually a dark nebula. This is a band of dust, roughly in the shape of a cone, that's blocking out the light behind it. Man, Robert, all we see is I think we see your headlight, and that's about it. We can't see you. I guess we're like,
Let me see.
what's the joke? We're like mushrooms. We do our best work in the dark.
I need a light on?
No, not necessarily. It'd just be nice to see you, to see your face every once in a while. But
Oh,
yeah, we all carry typically headlights like this just so we can see what we're doing, and we all have red lights. There we go. Sorry, Robert. I can't see anything. You want to talk about this image?
yes. I took the image probably last year. It's 15 minutes.
So think about that. We just took a 2-minute exposure and we had just stars and nothing else. Robert had to take a 15-minute exposure to be able to bring out that nebulosity. And even with that, it doesn't bring out a whole lot. Robert, do you have like the raw image you can show of what that looks like, what 15 minutes actually looked like? Sorry, put you on the spot.
That's okay. Now, this one is a black and white image. I did 1600.
Hold on. People are saying that they can't hear you on the stream. I don't know why. Oh wait, hold on. Here we
Can
go.
you hear me?
They're getting silence. Okay, go ahead and talk. I don't think anyone is hearing you, Robert. I don't know why.
Can you hear me?
I can hear you. I'm not sure what's going on. Great. Okay. So
Yeah, so Chris, you can't
mute my audio.
mute your audio.
Okay. Well, that's fun. All right. So we'll deal with it the best we can. Here we go. So Robert was saying that. Can you repeat that, Robert, one last time? Sorry.
This was taken with my ZWO 1600 monochrome camera with the HA filter to help bring out the hydrogen alpha channel. And this was probably a 45-minute exposure.
Wow.
1 minute each.
Oh, so wait. So this is a 1-minute exposure?
It's 1 minute exposure,
But 45
45 minutes of.
Okay, all right. So this is another technique that that we do is we'll take multiple images of the same object, and the reason for that is we're trying to level out the noise. The noise is going to be a little bit different from image to image to image. So instead, what we do is take a bunch of images and then average them all out together, align the stars in all the images, average them all out. Once they're all averaged out, then we kind of smooth out that noise, and we're able to get more signal out of it. So, but Robert, you took this from a dark sky site, right?
Yes, I went out to Thompson site.
Okay, so this is one of our dark sky sites. This is about 20 minutes north of Decatur, Texas. So for me, it's like an hour and a half drive. This is on a private nature reserve that the owners have graciously allowed us to use. We also have another site that is north of Ranger. It's about 2 hours or so west of Fort Worth, and they both have pretty dark skies. So if you join the club, you can actually use our sites. All right, not right now. Right now is not a good time to use our sites. We are on lockdown, so we are staying at home, and this is why we're doing this. So Robert, now we're looking at Rosette.
Yes, we're looking at the Rosetta Nebula, and it was taken with my optics red cat 1600 mono camera, and along with the HA filter.
So,
I think this was probably 45 minutes also. 1 minute exposure each.
And then using a bunch of software to actually pull out those details.
Right. I use SharpCap for capture. Then I use AstroPixel processor to stack and do some rough editing. Then for the final editing, I put it in Photoshop.
Okay. One of the things with images is that when we take them, they don't have a whole lot of signal. What that means is they're kind of flat. They're actually pretty flat, and I wish I had some images with me. Robert, do you have like a raw image, just a raw one?
Yes, I do.
That's it?
That's an unstretched image out of AstroPixel processor.
Oh, but that is processed though.
It's just out of AstroPixel processor, not with Photoshop.
No. I mean, but do you have anything which is like raw right from the camera?
Just a single shot.
Single shot out of the camera.
One sub exposure.
Yep.
Let me open up the FITS viewer.
Okay, because I kind of want to show what it looks like without any histogram stretching whatsoever.
So that's the black and white picture I took earlier.
Yeah.
And of course, you can stretch it, but this is probably what you're going to see about right there.
Yeah. So what you're seeing is pretty close to the raw image as it comes out of the camera. It's really, really grainy. There's a whole lot of noise going on. It's not a whole lot of detail going on. This is why we do a lot of images and we do a lot of post-processing. In fact, sometimes there's it takes longer to actually process the image after you get back home or when you come back inside than it took you to actually gather the image, the data for the image. There are some images which people stay out 4, 5, 6 hours, as long as they can, the entire night, imaging one object just to be able to get enough data. What else you want to show off?
Let me show you this one here. This here is the Horsehead Nebula. Again, it was taken with the ZWO 1600 monochrome camera with a HA filter. Taken 1 minute sub exposures. Took that for 3.5 hours.
That's a long time.
And when I ran this through AstroPixel processor, I had to wait at least 2 hours or so.
So
there was a lot of frames in there.
So that's an application that will do the post-processing. That's the stacker, right?
Yes.
Okay, so what that does is it takes all these images and stacks them one on top of the other virtually, aligns the stars so that one star is on top of the other, the same star in the image, and then it can go ahead and do the math and average out all those pixels. So the stars are still stars. They have a high signal to noise ratio, so they're going to have a high signal to noise ratio on the average, but noise is just going to be way down below, and that's going to get averaged out. And once it gets averaged out, Robert, can you zoom in just anywhere there on the nebulosity? Yeah, you can see you've got nice stars, and the background is really, really smooth. Those are some pretty sharp stars you got there.
Thank you.
Did you ever find that Ain't No? One of the Ain't No 100s? There's a galaxy less than a degree from the Horsehead. It's on the Ain't No list. I managed to get it with one of my images a long time ago. It's up north somewhere. It's really hard to pick out.
You got this one. Let me find it real quick. Yeah, this one.
So this is the Pleiades cluster. This is an open cluster, and what we're looking at with this one is that that reflection nebulosity I was talking about earlier. This is the remnant dust and gas from the formation of the cluster. Ooh, you did. You got a nice little galaxy right there. Is that an edge-on spiral? Is that what it's supposed to be?
I think it is, but it's UGC 2838. It is a galaxy that is far, far away from us. And it's 300 million light years away from us.
That's quite a bit of a distance.
And believe it or not, this was taken with my Red Cat with the 183 ZW Pro camera. This was an hour and a half with 1 minute subs.
You do the fast subs. I tend to do the long subs for mine. But then again, in these skies, and Robert, you're out in Weatherford, right?
Right.
So you've got a little bit darker skies than I do here down in Burleson.
Well, not necessarily. I'm in the Weatherford city limits, so there's light pollution here. This was taken out at Thompson.
Okay. And Thompson has pretty decent dark skies.
And Star Range does too.
Yep. So we typically will, if we want to do images like this, we typically do go out to our dark sky sites rather than staying at home. But right now we don't have that kind of an option. We do not own both those sites, and with the lockdown orders, we're staying put. This is Triangulum. This is Whirlpool.
Yes. It's
Triangulum Galaxy. Yeah. That is very, very nice. So, let's see. AstroPixel processor. Yeah, use AstroPixel processor. I use Photoshop and Nebulosity and PixInsight. But again, you can use a whole lot of different programs. This one's a really, really nicely populated star field. Go back to the previous one. So this is Dumbbell Nebula. It's named that because of it's a dumbbell. And then if you look at it, can you see it there? Can you see my mouse or not? I don't know if you can see my mouse. Yes, you can. Cool. Okay, so the red stuff around here and around here, this is hydrogen gas, and the blue stuff, this is oxygen gas. So this is a planetary, is that right? Yeah, this is a planetary. So this is different from the other nebulas that we're looking at, in that at the very, very center, there is a white dwarf. This is the core of a star, a dead core of a star. It's not doing any fusion. It's not doing anything. And all these stars within the nebula there, they're actually behind it or in front of it. But as a star gets older, it goes through a red dwarf phase, like our star eventually will. And when it can no longer burn hydrogen, it starts to burn helium. And when it does, it releases a lot of energy and it blows out the outer layers. Then it runs out of helium and it collapses down, and then it starts burning lithium. Runs out of lithium. It expands out when it's burning lithium, and then it collapses down again because it can't burn, or it's run out of lithium. When it collapses down, then it starts burning oxygen, nitrogen, carbon, and then it goes through and it stops at some point before iron. But it blows out those outer layers, and those outer layers just keep going, and eventually they form that planetary nebula. And it's called that because it kind of looks like a little bitty planet, a little round planet in the eyepiece of a telescope. So that planetary then is being lit up by this white dwarf. The gas in the nebula is being lit up by the core of this dead star, and we call that a white dwarf. It is the slowly cooling core. It's giving off a lot of ultraviolet radiation, and it's that ultraviolet radiation that is lighting up that nebula. Now we're looking at, what are we looking at? M13?
13, yes.
M13. This is a globular. You want to talk about it?
Sure. It's a M13, the globular cluster in Hercules. There's two galaxies. You can see one off to the right-hand side right here. Then there's another one about right here.
Oh, yeah.
A little itty-bitty one right here.
Little spiral. And a bigger
And
spiral.
you can see this one here, too.
That's pretty good detail.
Of course, every time when I go take pictures, I usually do a minute exposure time, 60 of them, or 2 hours or 3 hours. But with the M13, since it's a globular cluster, I usually do about 45 minutes, because you get plenty of data in that time, especially on stars. But when it starts talking about nebulosity, that's when you're going to have to start putting in the time for it to help bring it out. And again, this one was taken out at Thompson.
So a globular cluster is going to be a little bit different than the open clusters that we've been seeing. Globulars are conglomerations of hundreds of thousands to even millions of stars. They actually exist outside of our galaxy. They orbit our galaxy. And one of the neat things about them is that they stay together in that globular form. You have some stars that go way out and then come back into the center, some that stay close to the center. But there's something called evaporation of a globular cluster. It's kind of a neat concept. And you have to see this in other things as well. Let's say you're boiling a pot of water. The water never gets above 212 degrees Fahrenheit at sea level and standard temperature and pressure because the molecules of water that are too hot above that temperature evaporate off as steam and take the heat with it. Well, what's happening in the water that's left stays at the same temperature. What's happening in the globulars is as stars come in, if they're going too fast, they're ejected out of the cluster. They actually leave completely. They're just gone. They go out into intergalactic space. When they do that, they take away a little bit of energy, because this is a gravitational slingshot, from the stars that they just went close to. So those stars lose energy in their orbits, fall into a tighter orbit around the gravitational center of the globular, and the overall energy is decreased slightly of the globular because it is evaporating these really fast stars. The stars with a bunch of energy, high speeds, are leaving, and the net amount of energy in the globular is decreasing, and it all just stays compact. It's really, really, really neat. There are a lot of simulations you can find on YouTube about how that's done. But that is why these globulars can stay globular, stay as a round bunch of stars for billions and billions of years. And not just spread out, not like an open cluster does. Open clusters just don't have the mass. They don't have the number of stars that globulars do. Whew. Anyone got any images ready to go?
Let me make a real quick comment. 13, when you're looking through like a celestron or me 8-inch mid-cascading telescope with a 25 millimeter, maybe up to a 12 millimeter eyepiece, I mean, it just looked like you're in the space shuttle just sitting outside of it. I mean, it's just spectacular to look at.
It is one of the brighter, I think it is actually the brightest of the globulars that we can see from here. I just love those star fields. That's one of the things I like about my TeleVue is it's a short focal length. It's a 101 millimeter f5.4. If I put in a wide angle, low power eyepiece in there, I can get I think it's like about 4-degree field of view, 4.5-degree field of view, and I can just see, you just look at the Milky Way, and it's just thousands of stars in the field of view. It's quite lovely.
Now this is in Cassiopeia. It's called the ghost of Cassiopeia. IC 59 and 63. And this was just 2.5 hours worth. I did get something out of it, but it needs like 4 hours to help bring out the true image of it. But it looks pretty good because actually when you see a really good image of it, it fits the Halloween scheme. Because it's like a ghost that you see.
Robert, like some people are complaining about echoes. I'm not really sure how we can deal with that right now. I'm going to have to play with it for our next virtual star party and see if we can get rid of that echo, feed the audio in a different way. But you know what? Actually, maybe this will do. Maybe. I don't know. We'll see if this has an echo now. I don't think you guys can hear me. Well, no, this is not going to work. Yeah, I don't think that's going to work too well. But that's okay. We'll figure something out. Again, early days, technical issues. But that is pretty neat. And this is the bubble.
Yes. And this is M52, an open cluster right here.
Looks like a bubble to me.
You can definitely make out the bulb right here.
So you got noise in there as well. Well, and then there's the open cluster.
Well, with these pictures, these were my first working attempts with AstroPixel processor, and of course also with Photoshop. Yeah, you can definitely see the noise in it. How it's kind of walking right here.
Yes. Okay, testing something with the audio. Can you guys hear Robert now? Robert, can you say something else?
Testing. 1, 2, 3.
Okay, so let us know if you can hear Robert as well or not. If not, then I got to fix something else.
Testing. 1, 2, 3.
Ah, man, early days. All right, let's see. Let's go back. I'm going to go ahead and reshare my screen. Let's see if I've picked up anything. Oops. Yes. Okay, so I'm going to go back to here. All right, so back to Christmas tree. So turns out this is the bottom, and the cone is over here. So, it is what it is. I'm going to drag that over and over there. All right, so you guys can see me. And Robert, can you mute your mic? Hopefully we won't have echo at that point. Okay. Oh yeah, we're gonna go jump at something else. So we were looking at Christmas tree. Robert, are you still imaging right now?
I'm fixing to start.
Oh, fixing to start.
Yeah. Well, I've been trying to plate saw, trying to make sure I'm in the right area, but it's not working out.
Oh.
So if you want to go to the other guys, you can do that.
Yeah, George, Dave, do you have anything?
I am right now about 188 seconds out from the first image.
Okay.
But I can share the screen when that comes up.
All right. I'm trying to go to M3.
I've got something that's kind of ugly here, but it's, they're coming in. I'm shooting this the sliced onion galaxy, which is probably a little too small for the setup I have, but I've got a blob in the middle of the screen.
Oh,
And we'll see how it stacks up.
that's lovely. All right, let's see. Let's see if we can grab that comet. We're gonna go toward the set. No, I'm gonna go toward north. So there we go. Atlas. Nope. N1 V4. I want V4. We're looking at pan star. There we go. Here we go. So here we go. Here we go. Here we go. Let's grab this sucker. So we've got a comet. It will not look like this. Don't get your expectations too high. I gotta stop my guiding. Yeah, my guiding's not terribly great right now. It's fine. But I'm gonna leave it looping because we're gonna see if we can find the comet first in the guide scope. Is that a comet? Or is that a... I don't know what that is yet. Let's find out. That's probably a star. Anybody see a comet? I don't see a comet because we only have a one.
Sure it's broken up by now.
Well, it was as of yesterday. It was still visible. You could see the fragments and you could see a tail. So I don't think it dissipates that quickly. I don't see anything that's obviously a comet. All right, let's do it.
Are you doing live stacking, or are you just basically taking the same images?
Nah, I'm just taking images. So I'm gonna do let's do 20 second, but I want to do high ISO. Yeah, this comet. It'd be lovely if you let me type. Why won't you let me type? My fingers are nearly frozen. So you can take a quick 20-second exposure at high ISO. So we'll get lots of noise. I don't care right now. The reason why, I want to pull out as much information as I can to see where this comet is, and then center the scope on it. It's got to be somewhere. And I don't really care about guiding right at this moment. That could be it down here. Doesn't really like stars on the very edge there. Yeah, this could be it. Yeah, it doesn't want to do that. What I'm looking for is 3 tiny little fragments very close together and a little bit of a tail. I don't think that's it. Okay. All right, so let it refresh. That's not what I clicked. 14 degrees. What's that? I think that's the comet right there. I think that's it. So there is not a whole lot left. Let's go ahead and do a 60-second exposure, but I'm going to cut that way down to 800, and let's just start guiding. Pick a star, any star. I don't even know where it is on here. All right, just start guiding on that one. I mean low mass. There we go. All right, we're guiding back to here. Start new capture. I think that's it though. It's got the right shape. It's in the right position, and there's not really any nebula out there. There's nothing else out there that would cause that kind of fuzziness. So, yeah, that's all we got. But if it's broken up, it's broken up. There's not much we can do about it. Oh well, I was really hoping for a nice bright comet coming in about May. that'd be pretty spectacular. We could show off some really cool stuff, but yeah, we don't have that. So let's go ahead and give that minute 20 seconds, let it finish, and we'll go from there. Dave, you want to show your blob or not yet? You're on mute. I can't hear you.
There we go.
Yeah.
How about that?
Yeah, now we can hear you.
All right, so gonna unshare your screen and share mine, I guess.
Yeah, I get another minute. All right. Stop.
Oh yeah, once let's let yours come in. Let
Okay.
your image come in.
Oh, okay. All right. I'll go back to sharing my screen.
We got a minute left.
Yep. 33 seconds.
Yeah.
I really think that's.
Interested to see what we get out of time on that.
Yeah. Fortunately, my chip is cool at 14 degrees. So are my ears right now, even with the hat on. It's getting hard to type, and you can't really wear gloves and use the trackpad. So I'm trying to keep warm best I can. I think we all are right now. Except George. George is in his sunroom. George actually has his telescope outside, and his sunroom is about 5 feet away from his telescope, so you can access it very easily. I thought about running this from my office and remote desktoping into my laptop, but then I couldn't do all this wonderful stuff, and also if something screws up, I've got to run outside and try to fix it. I don't know. That's the only thing I can see in here at all in the field of view that would be like a comet, and there's almost nothing there. So I think it's probably fragmented. We'll see if other people have seen it tonight, if anyone else has images of it tonight online, if they're talking about it tomorrow, but there's nothing else that would cause that. I think we are in the right position. If it was there, we would have captured it. We were able to capture it at the last one. We could see it very, very easily. It hadn't broken up. It had a well-defined tail. We could see it wasn't gigantic, but you could easily see it. We were able to do a time lapse, multiple photos across the night, and I put that up as a YouTube video as well. So if you go to the channel and look at the YouTube uploaded images or uploaded videos, you'll see the time lapse there, so you can see it actually moving pretty decently across the sky, a small part of the sky, just over the course of a night. Just I think it was like an hour and 40 minutes is what we took the pictures from start to finish. So we could easily see it. All right, so we don't really have a comet. I guess we can take one more image. I'll just try 100 seconds. We'll do 100 seconds and see what happens with that. Let that go, so that'll be 200 seconds. Dave, you ready?
Yeah, sure. All
right, I'll do my stop share if you want to take over. So here now, y'all can see all of us. Yeah, you can see me in two different cameras because I have two different cameras set up. Ooh, that's a blob.
That's fine. How's that work? Does that work all right?
Yep, we can see it. It's a blob.
Okay. Yeah, it's a blob. I'm here in Sequence Generator Pro I'm using now. This is the Sliced Onion Galaxy NGC 33. It's pretty small. I zoom out. I'll show you. This is the whole frame that I'm taking, and this is at 666 millimeters. Got the E127 on it with a 0.7 focal reducer, so it's actually a pretty small target. But you can kind of make out the arms a little bit. I switch over to black and white view. I can change the stretch a little bit. Might be able to pick out some stuff. I'm doing luminance and then RGB images. This particular one is a red image. If I go back to the luminance, it's a little bit brighter.
You can see a little bit more detail. So this is a technique for taking color images with black and white cameras. So you can either have a color camera or you can have a black and white camera. Yeah, doing this. If you have the black and white camera, you put in filters in front of it. So like with Hubble. Hubble has black and white cameras. It doesn't have any color cameras. What it does is it puts filters in front of the chip that block out all but certain colors, certain wavelengths of light. And then you take an image with that. So you take a red one, a blue one, a green one, and then you take your luminance. Your luminance is basically what? Light pollution filter, and that's it. You just want the raw light from the object. And then you put everything together in an application, Photoshop or whatever you're going to use, and it will go ahead and get everything done for you and turn it into a full color image. Or you can go to the cheap way and just get a full color camera, just pop a full color on there, and it's just like a color DSLR.
Which is basically a monochrome camera with the filters permanently installed.
Yep.
Just a different color on each pixel.
And
so anyway, what I'm doing here tonight is since I've got quite a bit of light pollution out here, I'm shooting pretty much straight up right now. I wanted to push the exposure time up to about 2 minutes, just to get as much of the, if you look over here on the left, you can see my histogram, get it pretty far off of the bottom end. We'll see how this processes out. So far, I've got 10 or 11 images each of luminance and then red, green, and blue. So it's just cycling through each of the filters, taking one image and moving on to the next filter and just cycling through each of them. So however much I get tonight, I may end up with 50 images a piece, and I'll stack those and see what they look like. I'm not really expecting much. I was kind of wanting to find a target that was close to the meridian, the top of the sky, because that's when my telescope has to flip over so it doesn't crash into the pier. And last night I was doing some imaging, and I had a target where flip happened after 2 in the morning, and so I was asleep, but the flip was not successful, and so I didn't get anything after 2:15. So I wanted to make some adjustments and if it works. So I'm actually due for a flip here in like 17 minutes. So I'm hoping it's going to work okay. But anyway, that's what I'm doing tonight. I'm going to see how this turns out. The images coming through the single subs are not going to be fantastic. It is a small dim target, but we'll see how it stacks up. So anyway, yeah, I'll turn it back over to you, Chris.
Yeah, no pun intended, right?
Yeah, see how it stacks up.
So I'm gonna go back to my screen. Okay, so yeah, that's the comet. Wait, hold on. Let's go here. What that looked like, because that just downloaded. Come on. Come on. Is that it? I don't know why this is... Yeah, there we go. Okay. Yeah, so let's zoom in. Okay, so we have a tiny little dot right there. You can see it. I'm going to see if I can enhance it just a bit. That's the wrong direction. That's kind of the wrong direction too. Yeah, there we go. So let's go to luminosity. So just do black and white. We can see a little dot right there, right at the end, and a little bit of a tail. So that is all that's left of the comet. This is basically goodbye, Comet ATLAS C 2019 Y4. Oh well, you were pretty while you lasted, but we had hoped for for better from you, but here we go. So we were at least able to image the comet. We're able to actually see what's left of it. It's not nearly as nice as it was, but you know, it is what it is. I mean, there's no point crying about it. It's not going to get better. We'll just have to wait for the next one. But yeah, it's a bit disappointing, but it is what it is. So, all right, anyone have any questions or comments? You can see it there against the star field. I'm going to bring up, let's see, where do I have my, where do I have it? Oh, there it goes. Oh, man, that's going to be tiny. Oh, there we go. Yeah, you click it once, opens up 1,000 times. Where do I have it? Where do I have it? Where do I have it? These. My documents. No, pictures. Yeah. I was just going to see what I can dig up here by date. Bear with me all, sorry. So when do we take them? Oh no, that was a totally different one. We're going to look it up by date. See if we can get some pictures from last time. Nope. Where are my pictures? I don't know where my pictures are. I have no idea where they went to. Night. I don't know why my dates are so off. I have no idea why the dates are so off, but that's okay. See what that one is. All right, that's a comet. That's not a very good comet, but it's at least something. 60 seconds, 1 minute. Let's see if I can get something better. They're fairly large images. No. This is Orion Nebula. So that's the wrong direction. I want to go back. Down. 1 minute. Yeah, All right, one more try. Let's see how this one comes out. I wanted to see an image of the comet back from end of March. No, this is a galaxy. I don't know. All right, nuts to that. If you'd like to see the comet, you can always go to the YouTube channel and look at that video. You can also look at the time lapse, or you can look at the video from the last star party and take a look at that one. I'm not going to start digging through images and boring everybody, but here we go. We have an image of what is left of the comet. So, a bit disappointing, but it is what it is. All right.
Chris,
Yes.
hold on for a second. I want to show you something.
Okay. Let me know when you're ready. I will stop my guiding.
I need to share screen.
Okay, I will do this. Switch to you. Are you ready? Go ahead.
Okay, can you see my screen?
Yes, we can.
Okay, this is just what I did is I took one of the fit files, opened it up in AstroPixel processor, saved it as a JPEG image. So then this is where I'm shooting at, and look at all the galaxies in there.
There's a lot. All those, well, basically every one of those blue things is a galaxy.
Yeah.
That's a lot of
That's
galaxies.
that's a raw image right there from the camera.
Wow. No processing, nothing, right?
No. I made it right into a JPEG format so I could open it up in all plate solving.
So what plate solving is, for anyone who doesn't know, that is it's a technique where you take a computer will actually analyze the image, and it will find all the stars within it and figure out what those stars are. It's relatively fast, actually, as long as you have a decent database of stars. But it will, some applications like what Robert has right now, it will go ahead and mark on your image what each of those stars are, or the galaxies or nebula or whatever else you're looking at. On my telescope back there, I have what's called the Celestron Star Sense. This is a Celestron CGEM DX, and it's got a device called a Star Sense, and it's a camera attached to a tiny telescope. It'll take a picture of the sky, do a plate solve, move the telescope, take another picture of the sky, another picture of the sky. It'll do that 4, 5, 10 times, and then it builds up a map in its memory of exactly where it's looking at, and it makes alignment so much easier. I call it semi-auto magic. You hit one button and it does everything, and I don't have to spend the time doing the alignment. It'll do it itself, and I can spend my time instead working out technical bugs. So
this is a 30-second exposure.
That is not much time, and you're picking out a whole lot of stuff.
Or since I'm not using my other mount, I got to keep the exposure short on this one.
All right, fine. You want to do that? You want to play that game? All right, fine, Robert. Go ahead and give it back to me. I'm going to go to M90. I'm going to do a quick exposure of M90 so that I can pick out. All right, let's do that. So we're going to go back to here, M90, and we'll look at M3 in a bit. M90, 90. Here we go, hit that, and we will do center, go over. Where could it be? So it is in the east, and we'll do a slew to M90 at the same time. And if you look in the back, you can see the telescopes are moving. I just want to make sure that they don't get caught up on anything. All those, Well, that wasn't too bad. I didn't hear anything fall to the ground. Okay, all those green dots in there, those are all those galaxies. So we're going to be looking at M90, just one of them. Let's see, what can we pick up in the finder? All right, fine, it's in there somewhere. Let's grab that one, and I don't want a 3-second exposure, I want a 1-second exposure. Let's go ahead and loop it. Oh, wait. There we go. So I'll grab that star. When you're doing guiding, you don't typically want to too bright of a star, and you don't want too dim of a star. You want something that's going to be easy for it to pick up and keep on just 1 pixel and not lose. All right, so we got that. It's going to be M90. So we'll grab 100 seconds, 800 ISO. Sure, why not? All right, bye-bye, Comet. It's nice knowing you while you were here, but there'll be more. So this comet, Comet ATLAS, was named after an automated tracking survey. What we have is basically telescopes with cameras attached to them. They track the night sky, and they look specifically for near-Earth crossing asteroids. We want to know if anything is going to be coming towards us, because eventually something will be. We would like to know as early as possible so we can do mitigation. Send up a rocket. Do not explode it with a nuclear weapon, because all you're doing is, instead of getting hit by one big bullet, you're now being hit by a shotgun. What we want to do is push it out of the way. So that's either using a gravitational tractor, which is actually a real thing if you know how to do it, using a satellite, or you set off nukes nearby to use the radiation pressure to push it into a slightly different orbit so it doesn't intersect our planet when it comes by. We don't care if it comes in close, we just don't want it to, what's the term, lithospheric braking. It's definitely what we do not want. Litho braking is a bad thing in all cases. So we're taking the image. So anyway, so Atlas takes the images, looks for changes in the sky from night to night to night in the same part of the sky, and it finds asteroids, it finds comets, it finds a whole lot of stuff. And if it finds a comet, comets are named after their finders, even if it's an automated survey, such as Pan-STARRS that we had several years back, 2014. So they get named by the year of their discovery, and then a letter and number of the order in the year of when they were found, and then they get named Atlas or Pan-STARRS or the last names of the people who find them the first. It's like if you have one person who finds it and then calls it in and says, "Hey, I'm looking at a comet. Can you guys check it? Make sure it's actually a comet." That person gets the name, or the comet gets that person's last name. If you have 2 or 3 people who call in on that first night and say, "Hey, I found a comet," the comet gets all of their names. If you call in the second night, it's too late. You got to get that on the first night. You got to be the first one who finds it, not the first one or the first ones on the first night. First one on the second night doesn't count anymore. So we have a bunch of comets named Atlas. We have a bunch of comets named Pan-STARRS. They just differentiated by the year and the order that they were discovered. So Rod is asking, what was that application that does the plate solve? Robert? Still on mute?
Yes, I'm here. It's called All Sky Plate Solver.
All Sky Plate Solver. Okay, cool, because I need to get that as well. Ooh. Any of the questions? Oh, man. Let's see. Edward is asking about how I got into astronomy. Yeah, thanks, Edward. That's my cousin. He's the one down in Grandview, so we may be able to do something down there. Oh, what was that? Well, that sucks. Okay, and what that told me is that my guiding, my guiding stopped completely. Okay, so that's really bad. And the reason why it did is because, the mount hit its limit because this is at the meridian. I shouldn't have done that then. All right, we'll wait on that. Instead, we'll do M3. All right, fine. Well, that was a mistake. So you can see all these comets here in the field of view. M3. All these little bits here, these are all comets, but they're so dim that there's no point even looking at them. Slew to M3 and center. Where is M3? So M3 globular cluster. I'm hoping we'll be able to see it in the finder. There we go. That'd be right there. That is not a comet. That is a globular cluster. So for people who didn't see the last one, we're looking at objects that say M3, M35, M101, M90, all that stuff. What we're saying is Messier 3, Messier 35. And Messier is the name of a catalog of stars. A catalog of various objects in the night sky. It's gonna look something like that. So, back in the 1700s, there was a French astronomer named Charles Messier. He was a comet hunter. That's all he cared about. Nothing but comets. Didn't care about anything else. Didn't care about planets, the moon, the sun. Nothing else. Only comets. He wanted to find comets, and he kept finding stuff that wasn't comets. It was fuzzy stuff in the sky that wasn't a comet. It didn't move night after night after night. And so he created a catalog for fellow comet hunters of 110 objects in the sky that he wanted to make sure that no one else made the mistake and said, "I found a comet," and it turns out it wasn't. and these are they turned out that these are some of the brightest non-stellar objects in the sky. There are a couple of stars, a couple of binaries. I think there's 1 or 2 binaries in there, but they're open clusters, they're globular clusters, they're nebulas, they're galaxies. They're really, really interesting things, and they're very bright in the sky. It's stuff that you can pick out with your telescope. And so the catalog is named after him, which is kind of funny because none of them are comets. And he is remembered not for finding comets, he is remembered for having the Messier catalog. So now we're still doing imaging, 100 seconds. Yeah. It is getting chillier. Let's see what does Google say the temperature is? Oh, it is 47 degrees. It's got to be colder than that. It's got to be colder than that. Whoa. At least it feels colder. So 82 seconds. 80 seconds left. All right, that's not too bad. It's not bad at all. So looking back here, this is one of the globulars that we talked about earlier that these orbit our galaxy. I don't remember if we know their origin or not. I know that we do actually have some globulars that are going around the Milky Way that we cannibalized off of another galaxy. I don't remember which galaxy it was. I want to say it was the Sagittarius Dwarf Galaxy. No, probably wasn't Sagittarius Dwarf. Maybe been some other one that the Milky Way cannibalized billions of years ago. So galaxies cannibalize others. And we're actually moving towards the Andromeda Galaxy, or maybe the Andromeda Galaxy is moving toward us. In any case, we're getting closer and closer together. And in a couple billion more years, the two galaxies will merge. But they don't smash into each other. What they'll actually do, because galaxies are mostly what? Open space with a bunch of stars in it, will pass through each other. And then they will pass through each other again, and again, and again, and again, and again, until they settle down into an elliptical galaxy. Instead of having nice spiral arms, it'll just be a big ball of stars. And when that happens, a lot of stars are going to get thrown out, just like the evaporation with globulars. The fast stars will have when stars come close to each other, especially if they're moving in opposite directions. There'll be a gravitational assist, so the bigger star will probably lose some energy. The smaller star will be thrown off in another direction. If they're passing close to each other, you have kind of the same thing. Come on. Why you no guide? Well, that's a globular right there, but geez, what is wrong with my system right now? Something's not quite right. Something's definitely not right. So I'm going to do this. Let's do a 10-second capture, see what we can find. What is going on? Oh. Well, normally I would say, I don't know what's going on. I know exactly what's going on. I totally forgot to clear my calibration because we switched meridian. We went over to the other side, and now I have to do this. I have to train the guider again. I know there's a way to do it. I know there's a way to do the flip automatically somehow. I just don't remember what it is, and honestly, I can't be bothered to do it when it's 10:55. There's a globular, probably. Jeez. All right, I'm gonna give it. The training. It's still gonna be training for a couple more seconds, but I wanna. Yeah, we're off, so I'm gonna recenter it. Slew to that. I probably should have waited and not slew to it while I was doing training, but yeah, that was a bad idea. Bad idea. But we can see the globular right there. Loop, loop, loop. Come on, baby. Are you looping? It's looping. Okay, good. So, guide on that. All right, so this is the globular in the finder. We'll wait until it's done training so we can get a better image. Yeah, this will be more in the center in the field of view, and we'll see it in there. Yeah, let's just have it on here. We can see it there. So it's small, but it's bright enough on a 1 second exposure. You can easily see it in the guide scope in the finder. How much more? Backlash step 2. Okay, so it's got a little bit more it's got to do. It's not too bad. Edward says, does cold affect imaging? Yes. Cold makes imaging better because the chips are cooler. There is less noise. You get much better images when it's cold. In fact, with typical astronomical cameras, what they actually have, and I don't have one right here. It's back over closer to my house. Astronomical cameras typically have a thermoelectric cooler on them, or stacked thermoelectric coolers, and so you'll have a hot side and a cold side. The hot side you put a big old heat sink on and some fans, and the cold side you put right up next to your chip. So you're getting the chip down really cold. You want it as cold as possible without dew forming on it, so you typically chill it down to just above the dew point. But if it's all sealed up, you can get it a lot colder than that. But again, you just don't want dew on it. You don't want frost on it. There we go. So now it's tracking. Let's get an image. Let's get duration. How about 30 seconds? 30 seconds at 800. That should be fine. We'll be able to pick something out with that. So you cool down your chip. You get less noise. Less noise means you get more signal. More signal means you have better images. So cold is very good for imaging. It is not so good for astronomers. And my hands are really chilly. I don't know how you guys are over there, Dave and Robert. I'm not even going to ask George. George is sitting inside his sunroom.
It's cold out here.
Yeah, it's not much fun, is it?
No.
Now think about this. Typically, we are going to be out at a dark sky site. So we're not at our house where the warm house is just a couple steps away. We're typically out somewhere where it's another hour and a half drive to get back home. So Dave was using a program called Sequence Generator Pro, which actually lets you do everything, set up your entire imaging session from one application. You control everything. You hit the button, and then if everything runs well, you then get to go inside, take a nap in your car, go back home, whatever you want to do, and you'll come back to completed images. There we go. That's not bad. Let's push it. I'm going to do a 60-second exposure. While that thing's going, we can take a look at this thing. It's not quite in focus. That's all right. But what we can see is a bunch of stars. And actually, they're red. Oh, I guess I should have mentioned that before. These stars are fairly red. They're not white. We can just switch it to luminosity and get rid of that. Because this is a modified camera. It is modified for astrophotography. It's a modified Canon T3i with no filters on it, and so every picture it takes is going to be really red because I'm trying to get that near infrared light, that deep red light from hydrogen emission nebulas. So if I take a regular picture with it, just anything during the day, it looks like a old picture from the 70s or the 80s where the green and the blue print colors have faded out and all you see is red. It looks exactly like that. And I can actually put a infrared filter on that and take infrared images, which are really cool. Okay, so one more minute while this thing goes. Geez, 11 o'clock. George, you got anything for us?
Unfortunately not. I'm troubleshooting. I don't have a pole star to look at, so I'm trying to use the software, and it's a learning curve for me.
Okay. And that is yet another problem with amateur astronomers, or a problem that we have is you get ready to do your imaging, and you end up doing technical troubleshooting, and then you don't take images. I spent 2.5 years doing troubleshooting on my mounts, trying to figure out what was going on. Why couldn't I do tracking? Why couldn't I do tracking? Why couldn't I take decent images? What is going on with my system? Until I finally figured out what was going on, and it was my guiding settings. It took me 2.5 years to figure out why my guiding settings weren't right for my camera, my guide scope, and my mount. It all has to tie together. Yeah, 2.5 years. So there we go. Now we got a brighter core. We have some more stars that came out, especially with the 800 ISO. Let's get longer duration. I want to do 100 seconds, and then, because I can, we're going to do 140 seconds and leave it at that at 800. We'll do start capture, and what I did is I actually put in 2 images in there. So it'll take the first image, and then it'll jump right to the second image without me having to wait in between. It'll do it automatically. I can add in a number of exposures for the exact same settings, but I wanted 2 different ones to see what we can get. So we're looking at the core of this globular. I have no idea how many stars are in there. There's probably tens of thousands to 100,000 stars just all through here. But you can see there are really bright ones, and then you can see there are really, really dim ones. So the dim ones are going to be typically older and smaller, give off less light, so redder. The bright ones that you can see, hot, younger stars, and they're going to be big, bright blue and white, and those are the ones that are typically lighting up the globular. That's what you can see. You can't really see the dim ones terribly well, at least lower exposures. It is not a matter of distance. If you look at it percentage-wise, the stars that are on the other side of the globular as compared to the stars on this side of the globular, there's not much difference in distance between them when you compare it to the length, to the distance from here to there overall. So let's get some information on it. We can see exactly what it is. Description. So here we go. 500,000 stars, 500,000 stars, blah 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 blah, da 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 da. Position sky, position space. I want to see this. Position space. So we're looking at something 35,000 light years away. Our galaxy is what, 300,000 light years across, something like that. At least the visible part of our galaxy is about 300,000 light years across, 320. Yeah, we keep updating it because we get more and more information, and it turns out that the actual size of our galaxy, if you count in our galactic halo and the dark matter halo around the galaxy, I think it's something like 10 times bigger than that. So it's like 3 million light years across, something like that. 3 million light years across from one end to the other. So kind of big. I want to say it's 10 times. Now I don't remember. Now I'm second guessing myself, and I could be wrong. I'm wrong often, and if you correct me, I'm absolutely happy. I would rather be wrong and be corrected than think I'm right and not be. Here we go, another 40 seconds. This is actually pretty. We have nice round stars. I could do better. I think I could get my focus a little bit tighter, but for now we're good. We can make out stars in the background. The smaller stars, they're actually coming out of the noise pretty decently. The camera is cool, 16 degrees Celsius. Yep, that's pretty cool. I think we were averaging about 24, 25 at the last virtual star party. So it's significantly colder. Couple more seconds. Anything. There we go, even brighter. So we can do longer and longer exposures and pull out some of those dimmer and dimmer stars, but we're going to be overexposing the core. That's a problem that we're always going to have with Oh, let's reset this. There we go. Back to there. That's actually a little bit better. We can see down at the core. I guess I just had the histogram set. So yeah, we can see some of the stars down in the core. We can see them all around. I had boosted this so you could see some of the dimmer stuff around here. It'll stand out a little bit more, but it overexposes the core. Just reset it. The core is nice and defined. You can see a lot of stars all through there. It's really, really pretty. When you look at it through a telescope with a good eyepiece, it looks like just little bitty diamonds just scattered in the field of view. It's very, very pretty, and you can stand out here when it's not this cold and just look at it for hours and hours and hours. We were looking at M13 earlier from Robert's images, and that's the brightest of the globulars in Hercules. And you don't even need a very large scope to see it. You can even see it with smaller 4.5-inch scopes pretty well. This we're imaging with an 8-inch scope. So the bigger the scope, the more light it gathers. So the faster you can take an image of similar quality to a smaller scope. But they're typically going to be made better anyway, so you're going to get better images. You also have resolution issues. The smaller the telescope, the less resolution it has. There's something called the Dawes limit, DAWES, and it's a general rule of thumb that says that the maximum magnification that you can pull out of any optical instrument is 50 times per inch of aperture. So if you have a 50 millimeter scope, or let's say binoculars, 50 millimeter binoculars, the very possible best, assuming everything is perfect, is 100x. So looking at telescopes, this is an 8-inch, so 8 times 50. The absolute best that you can have would be 400x magnification. So you'd have to calculate it with the focal length and your eyepiece and a bunch of other stuff. And honestly, I never bother with it. I'm more concerned with the field of view and how it looks, as opposed to how much can I magnify this by. But usually that's the first question that someone asks, is how much is it magnifying? And then I got to pull out my calculator or my phone and calculate exactly what the magnification is and tell them, oh, we're looking at 127x. And I don't really care. I just care about the images. And when you're taking images like this, you don't care too much about magnification in the raw sense, because you're going to be zooming in and cropping the image anyway, no matter what you're looking at. We typically don't do full field images. There, you can see all around it. It is fairly big. Now, through this telescope, if we were looking at the full moon would be about that big or so. And if we look back here, the full moon is a half a degree. So with this one, yeah, I believe this is the half a degree circle around it. So just picture how big this would be in the sky if you could see it naked eye. If the surface brightness was bright enough that you could easily see it naked eye in a really, really dark sky, like out in Big Bend or middle of nowhere, Utah or Nevada, this would be just smaller than a full moon. But we can't see that very well. It doesn't have a very high surface brightness, so you can't really see it well naked eye, especially through suburban skies. Edward Fries, what is a dark matter halo? Okay, so 90%, let's flip that around. What we see when we look up into the sky, what we see in all the galaxies, all the stars within the galaxies, everything that's bright, everything that's shining, everything that we can see, the visible stuff, is 10% of the mass of the universe. 90% is missing. It's dark. So it could be lots of things. It could be WIMPs. What are WIMPs? I forget what WIMPs are. We have WIMPs and we have machos. Machos are massive halo objects, something like that. Think of them as they're big objects, but dark objects somewhere in the galactic halo. WIMPs are weakly interacting massive particles. These are different ideas for what dark matter could be composed of. Lots of planets as well. So planets seem to be very, very common when we look at data from Kepler and all the eclipsing star data that we're now pulling in. If we have so many planets, planets are going to make up a large or at least some percentage of the mass of the universe, but we're probably not going to be able to see them very easily because they don't shine with their own light. So dark matter is a general term for anything, any mass in the universe that isn't glowing, that it's not emitting its own light that we can easily see. So it could be some stuff that we don't know about. It probably is stuff that we don't know about, but we don't even know how much of whatever it is it could be. Right now it's just an unknown. So, but we're doing more research into it all the time to find out more and more information. Here we go. Here we go. This is at 140 seconds, so it went from 100 and 100 seconds, and all we did was add in a little bit more time to 140 seconds, pulled out additional data out of it, and I think at 140 seconds it's already too much. We're not pulling in any additional data out of these stars. We have a little bit more streaking. I think if we go back to here, we're actually seeing a better result. There's more contrast with the background. I can force more contrast as well. Yeah, it's too much. Yeah. So we can see it a little bit more defined, but if I just do reset, if I leave it as it is, you can really make it out in the sky. It's really pretty. And it's stuff that you can see with a small telescope. Last time we talked a little bit about telescopes. If you are new to astronomy, if you haven't had a telescope before, if you haven't been out looking at the night sky, I would highly recommend that you not go and buy a $100 telescope or less. Typically, they're not made very well. They don't give very good images with their through the eyepieces. The eyepieces are usually really, really cheap as well. So narrow field of views. All the instruments that you're looking at today, the images that Robert used, the images that George would have been taking if he wasn't troubleshooting, the images that Dave was taking, these are all large telescopes. They're large telescopes. They're expensive telescopes. They're expensive cameras. You don't have to do that. You don't have to go that route. You can go with cheaper stuff. If your budget is $100, I highly recommend getting a pair of really, really nice binoculars. They're going to last you a lifetime anyway. I still use my binoculars often when I go out to the dark sky side. I take them with me because they're really easy to go just find stuff in the sky. And, you know, I know it's there somewhere. Let me put the binos and find it that way. Then, if you're going to make the jump, I would look at buying a probably 8-inch or 10-inch Dobsonian telescope. They're really easy to use. They go up, they go down. The Dobsonians are named after John Dobson, a very weird old former Buddhist monk who was kicked out of the monastery in San Francisco because he kept sneaking out to build telescopes out of junk and then give them away to neighborhood kids.
Hey, Chris?
Yes.
One thing about equipment is you could look on cloudy nights and Astromart. They're pretty good deals on like Dobsonians and stuff of that nature.
You can look on Craigslist. OfferUp is another one, but I highly recommend Cloudy Nights. It is free. It's completely free. Astromart has really good stuff, but there is a fee to join. Cloudy Nights, you just sign up and you can go. It is owned by Astronomics, who is they're a telescope shop outside of Oklahoma City, in Norman, Oklahoma. They're very, very good. They've been around for 40 years? Been around for a long time. I highly recommend them as well, but if your budget does not include buying new stuff, Cloudy Nights, I buy most of my stuff used. Used to buy most of my stuff used. I don't buy a whole lot now at all. But you can get really, really good equipment, and you can learn how to use it. The Dobsonians, it's the old joke is, John Dobson, you say they're yogurt powered. You eat yogurt, and that gives you the energy to move the telescope. You move it up, you move it down, you move it left, you move it right. It's really, really simple to use. Okay, I got like police cars or something, or fire truck going by. I don't know if you can hear that, but it's joys of being outside. So back to telescopes. I would recommend an 8-inch to a 10-inch Dobsonian. That'll run you new 3 to 500, used 400 to 600 new, used probably about 200 if you can find it, to about 400 500 for the 10-inch. I would look at how much are you willing to actually use it. If you have a 8-inch scope that doesn't weigh a whole lot, that you can keep in the living room off in the corner, it's a grab and go scope. You pick it up, you take it outside, you put it down, you can be observing in 5-10 minutes, easy. If you have a scope that takes you 2 to 3 hours to set up, you don't want to drag it out. You just don't want to drag it out. You don't want to leave it in the garage. You want to leave it in the office. And it's like, I don't have the energy to take it out tonight. Even though it's a lovely night, I don't have the energy. Look at how big your car is, what you can take with you. Would an 8-inch telescope fit in your car? Would a 10-inch telescope fit in your car? If it won't, well, there's not really much of a point in getting it, because you're not going to be able to transport it to some really nice sites. If you have, if you're in a dark sky site already, if you live well outside of town and you want a nice telescope, you can do a permanent mount. You can get a really, really big telescope, and you can put it in your own little observatory, or have it in a shed, roll off roof if you want to, or just put the damn thing on wheels, wheel it out into the driveway when you want to use it, wheel it back when you're done. These are all options, but you have to decide for yourself. The reason why I suggest 8-inch to 10-inch every single time for Dobsonians is because it doesn't matter if you catch the horrible disease called aperture fever and need to upgrade to bigger and bigger telescopes. An 8-inch telescope will last you a lifetime, because you can always have that. It's really easy to grab it, pick it up, take it with you, and I'm too tired to drag out the 16-inch. Believe me, I've been there. When your tube alone weighs 90 pounds and the base weighs another 70 pounds, you don't want to drag that thing out. So the 8-inch comes right out, and mine is small, it's light, it's collapses down to a box, and I can put it in the car and put the poles in there and take it out to wherever I want and set it up in 5 minutes and be observing in 5 minutes. So it doesn't matter how big your telescope is later on. A 8-inch to 10-inch will last you a lifetime. You just have to decide how much you're willing to carry, how much you're willing to drag along, and you make it as painless as possible. The more painful it is to set up, the less you want to use it. I can tell you, when I had the 16-inch, I took it out twice at home, once to the dark sky site, and once to a star party. And to take it out to the dark sky site or the star party, I had to go borrow my parents' minivan, because it would not fit in my SUV. The tube was just too long. And 90 pounds, that's a lot for my wife and I to carry around. So not easy to use. So again, yeah, I didn't get a whole lot of use out of it. Actually, I sold it back to Ben, the guy who sold it to me in the first place. He really wanted it back, and I was ready to get rid of it. And I actually used the funds from that to get some of my equipment here, the mount. So the mount weighs not quite as much as that big Dob, but it is a pain to get set up. Do we have anything else? Dave, you want to show anything? Robert, you want to show anything? Otherwise, we can be done for the night. It's getting cold, and there's an airplane overhead. I live near Spinks Airport, south of Fort Worth, and we are on the landing pattern right over my house. So we have planes coming overhead typically. Sorry, go ahead.
I am done. Got work to do on my my automatic flip, and faulted out again for a different reason this time.
It's always something.
It's always something. So it's off to the discussion boards tomorrow going, hey, what do you guys think?
Okay, Robert, you got anything you want to show us?
Well, I'm still on the pictures. We're still taking pictures, and I'm just waiting for it to count down.
Okay, I'm going to look at where is... I'm going to have to flip it. Okay, I'm going to see if I can get M90 just for kicks and grins. It's 11:22. We've run over. Whatever. M90. I want to see if this will do it right. Will it go the right way? You know what? Forget that. I'm going to use the hand thing. I want to see if it does it a little bit differently. So I can go to Deep Sky, Messier 090. Okay. Maybe. Okay. There it is. M90 Galaxy. All right. So we're not quite at meridian. That's what we're looking at now. M90, that's pretty faint. But we'll see what we can pull out. I'll do a stop. Loop it again. Pick out a different star. Here we go. Start guiding. We're not seeing anything in here because these are fairly low surface brightness galaxies. And I will do, let's just do 60 seconds, what we can get with 60 seconds, higher ISO. We typically don't deal with ISOs with the astronomical cameras, but all right, let's see what we can get with this one. So, that's a pretty picture. I like that one. I don't like it in color just because this camera isn't the right one for color, and my other camera doesn't want to initialize with the application. I don't know why. It's just being ornery right now. And I lost another DSLR, so I have to get that one fixed or check out why it's not working. But it's always something. It's always going to be something.
Hey, Chris?
Yes.
The gain on like dedicated astro cameras start up at 0, and I think we can go up to 800 with the ZBO brand.
But it's not exactly it's not correlated with ISO, but it does the exact same thing. It's just not called ISO. It's just regular gain.
And like if you're out there at Mount Davis, you can probably run a 0 gain because there's very little light pollution. But like here in the DFW area, you want to run 100 to 200, get a quick picture, not to oversaturate image, have kind of reduced noise too at the same time.
Do anything about this? I really can't do anything about that. That's fine. Yeah, let's see.
It's cold out here.
It is. And when does the moon rise? It should be rising probably pretty soon. I don't see any. I can't tell if the eastern horizon's getting lit up, but 123. Oh, no. Okay, it's not going to rise for a while then. Yeah, there's no point in waiting up for the moon. I'm not going to wait up for the moon. I have to work tomorrow. So earlier, Edward asked, how did I start in astronomy? I was always interested in astronomy from a little kid. Bought my first telescope at 19 because my parents wouldn't buy it for me. And then I built a telescope for myself. I built a 10-inch. Then I designed and with my dad built a pair of 8-inch telescopes. And this is a galaxy. This is M90. Yeah, that's it. What we're seeing right here is the core of the galaxy, the very, very center. And there's going to be a black hole in it, just like there is in the core of pretty much every galaxy. Edward's asking, this is, you can see up here, this is a Canon T3i. And the reason why we use T3is is they're really, really good about their noise. Earlier models and later models had a lot more noise to them, but the T3is just seem to hit like this nice little sweet spot on the chip, and they have typically less noise than other cameras. But you know, people do full frames, people do lots of stuff. If I move it around, let's see if I can do some of this. I'm gonna take 120. Just no. I'm gonna drop this down 120, and I'm gonna take another image at I go 180. Just 3 minutes. That's gonna be too much. Yeah, 120 is gonna be good. At 3 minutes, we're just gonna see way too much sky glow, or not sky glow, just light pollution. So if I move this around, you can kind of start to see a little bit of detail. There's a dust band through here, and there's maybe an arm, something like this. There's something here, but we can definitely see a dust band in here. If I took a lot more images, like Robert is doing, just taking a large number of images and stacking them up, I can get rid of that noise, I can get more signal out of it. And it'll just be a better image instead of just taking one image and leaving it at that. Also, I would be playing with my focus a little bit better. I'd get a little bit better focus out of it instead of what I'm doing right now. So I get, you know, a little bit sharper stars. I would also definitely switch over to a dedicated astronomical camera instead of using a DSLR. DSLRs are really, really nice. They're fast. You can do a whole lot of cool stuff with them, but if I'm going to be doing dedicated stuff where I'm taking pictures of galaxies or nebula where I want the chip as cold as possible and it's not a cold day, then I want something with a cooler on it. I actually have a cooler for the DSLR, but it's kind of wonky to put on, and it adds on. There's not a whole lot of vibration that it adds, but it's just wonky, and I don't feel like messing with it now. I've got to strap it to it and do all sorts of stuff, and attach it to the bottom screw. There's just additional work I don't want to do. So we're another 20 seconds left on imaging, and then again we'll take another 120-second image for the noise reduction, and hopefully it'll be pretty. We'll be able to see a little bit more detail out of it and get something before Robert's got something. Is that right? It is getting cold. There's a very, very... If you want to.
On a few frames?
Sure.
Okay, let me...
You want to take...
start working on it.
Okay. We don't have a whole lot of time left. I'm getting to the end of how much I can stand right now. Like on radio, they call this dead noise. No, dead air. It's dead air. Oh. So I have a number of cameras, not just the DSLR. So I have 2 dedicated astronomical cameras with coolers on them, and then I have 3 non-cooled cameras. One is like basically a planetary scope. It's really good on planets and high resolution stuff like that. It's a really, really small chip, but it's got a lot of pixels on it. It's full HD. I have another one which is a little bit better, and then I have this one on here is that I'm using to guide on right now is actually a black and white camera, but it's much higher resolution. This is 6 megapixels. The other one like 2 something megapixels. So you can get decent images even out of lower megapixel cameras, but this one is it's a slightly bigger chip, but a lot more pixels. They're really small, they're really fine, and we actually use this one on our hydrogen alpha scope that we have for the club. So we have a number of club telescopes that we use. Most of them are at the dark sky sites. If you join the club, you do not actually need your own telescope. You can use one of the club scopes. We have a number of Dobsonians out at both dark sky sites, so you can just go out there with nothing. And there are eyepieces out there, and there are telescopes out there, and there are star charts out there. But I highly recommend you use an application on your phone. It makes everything much, much easier. Then you can just go out and do observing. We also have 2 telescopes that are basically library scopes. If we're not using them for outreach, which we're not right now, you can use them, you can borrow them and use them for yourself. We have a 11-inch Celestron CGE 1100. Yeah, so it's a Schmidt-Cassegrain 11-inch on a fork mount. You can use that one, and we take it out to, or did take it out and will eventually take it out again to our star parties. And then we have a hydrogen alpha scope for observing the sun. We can look at prominences, at flares. We can see a lot of surface detail, and that is a scope that we take out for daytime events, so people can see the sun when the stars aren't out. There's at least something that we can show, as opposed to posters and talking about it. So again, we can see this kind of dark banding here. If I move it around, it becomes a little bit more obvious. There's stuff out here like that, roughly. But again, it's not a very long exposure, and we are in the city. So if I want a lot more detail, I would go out in the middle of nowhere, and I would try to get as dark skies as I can, and then keep taking pictures and keep taking pictures and keep taking pictures, and see what I can uncover. Come on. Come on.
Bruce?
You ready?
It's running right now.
Okay.
10 pictures, and of course I threw in a couple flats and dark to help kind of clean up the image some.
Want to take over?
Sure.
I don't know why I'm mirrored in my cameras. It looks weird.
Right now I'm running AstroPixel processor. I've loaded up 10 frames, 10 light frames, and 5 darks, 5 flats, 5 bias frames, and those there help subtract the noise out of the picture, along with the amp low and other little anomalies like dust bunnies and stuff that happens to be on filters or on the sensor. It's going to take probably a few minutes to run through this, but right now it's doing a quality score on these stars. The higher the number of the quality score, the better the stars are. And right now they're running about 3.13, which is pretty good. One time I've gotten down to 1.68, which is very good. Nice, tight, little round stars. Guess I should turn the light on.
Oh, we can kind of see you. You're showing up. The glow of the screen.
You need a little buddy heater, Chris.
Yeah, I'm just...
It seems like we're almost completed with the stars here on the star analysis. We're going to enter register. And it usually don't take long either.
All right, while this is going, I'm gonna go get another jacket. So I'll be right back.
One thing about AstroPixel processor, you can add more memory or allocate more memory from the laptop, so it will fly through this stuff. Of course, the more files you have, the slower it runs. This is a pretty good program. At first I used Deep Sky Stacker. It was okay. Of course, it's free software. It works okay. I think it works better for people with DSLRs than it does with dedicated astro cameras. But of course, with this software, you could either buy the renter's license for a year or buy the lifetime license for it, which I'll probably do when it comes up due August, I believe. And of course, I was thinking about using Pixel Insight, but to me, it's just way too complicated. And it's cold out here. We're on the last stage of being integrating.
Just thinking another day or so, probably be back up to 90.
Yeah, actually, it'll probably be tomorrow.
Thursday, I think, is supposed to be clear.
That's doing that. I'm going to do this. Pass the time. Kind of show off some of my moon pictures.
Oh.
It's good to get the moon around like just a few days after the so you can get the terminator frame on the craters. That gives you the best visual effects.
Ooh, pretty.
I use my 290 ZWO camera on this, and I use my Plus from an 8-inch Smith-Cassegrain telescope. Regstack 6 or Photoshop for editing. It's pretty amazing how you can get details out of these cameras nowadays. Seem like some of the people on Facebook, I swear they have a drone in lunar orbit taking some of these pictures. And of course, we got the crater Copernicus. We got a mountain ridge over here to the right of it. We also got some other mountain range here too. I'm not sure if this is Plato or Plateau or...
I don't remember.
Of course, here's the mountain range, and of course, Copernicus is further over to the left. There it is.
Got it?
What's in the oven?
I see galaxies. I see a lot of light pollution.
Yeah.
That's M90 up there? Yeah,
Yes,
that's like M90.
M90 right here.
So we were seeing that dust band below or something.
Well, since this is only 10 pictures, it's really kind of see the dust lane in it. There's probably another galaxy right here. Good.
Ah. There we go.
That changed a lot. This is one of the big sellers about astropixel processor is the light pollution. Just put a few little squares here and there to calculate.
Wow, that's pretty cool.
Extremely cool. So you see a lot more galaxies. Of course, there's more of a purple tint than anything to be taken care of. But you can see all these galaxies through here. Even though I didn't get part of the, what's that name?
Markarian's chain, yes.
It's further off to the right hand side, I believe. But you can see all the galaxies in here.
It's very nice.
Right there.
Yeah, if it's not a point, it's a galaxy.
And like what Chris was saying earlier, that all these galaxies are probably, some are close to us, some are far away.
They're just flat to our field of view, to how we can see it.
Right.
But it's very nice. Thank you, Robert.
No problem, Chris.
I'm glad we could do this tonight. I'm not glad it's so cold, but I'm glad we could do this. I'm sorry, George, that you couldn't get your stuff up and running.
That's okay. Next time I'll join you outside. I think I'll be doing it from the front where I can actually get to them.
That's why I like my backyard now compared to the old house, is I have much more of an open sky. I can actually see Polaris pretty decently and do my alignment. Oh, let's see.
Every winter I have a place for it and start from the backyard. But then again, there's no leaves.
Well, let's see. I'm gonna take this down. I'm going to stop this. And I'm gonna say, again, I'm Chris Wojnicki. I'm the president of the Fort Worth Astronomical Society. I am very cold, and my wife has reminded me, what are you doing out there? You're working first thing in the morning. So I gotta go to bed after I pack up all this stuff, because I'm actually using one of my monitors tomorrow at 8 o'clock for work. So thank you everyone for joining us, and I'll do the usual thing of the thing that YouTubers say is like and subscribe down below. Thank you to everyone who joined us. Let's see, where is it? I have to do that. Here we go. We have Robert and Dave and George joining us. Thank you again, everyone, and have a good night. And next week, 7 o'clock on Tuesday is our club meeting. So the stream will be on YouTube, and you can go to Facebook and you can find the link there. Thank you, everyone, and good night.
Hey, Chris.